Good morning, one and all. Firstly, I would like to thank Ontario International Development Agency for accepting my paper and for giving me a chance to present in 22nd International Conference on Sustainable Development 2025, which is going to be held at Colombo, Sri Lanka. So, coming to myself, I am architect Karthik Chadalavada, scholar and working as assistant professor in Department of Architecture, School of Planning and Architecture, Vijayawada, which is an institute of national importance under Ministry of Education, Government of India. So along with me, I have my co-authors and my PhD guides, Dr. M. Kranti Kumar and Professor Dr. Srinivas Daketi, who are again the faculty in the same institute, School of Planning and Architecture, Vijayawada. So coming to my title, Optimizing Passive Design Strategies in Warm and Humid Climates, a holistic framework for green building rating systems. So before I would like to go further, so the reason for me to start this particular research is nothing but we have a wide range of green building rating systems across the country and even across the globe. So among all these rating systems, so I was looking forward towards passive design strategies. So how much is a percentage of passive design strategies being emphasized in each rating system? And the research further goes on in evaluating whether all the research all the green building rating systems are doing even amount of the numbering for this particular passive design strategies in this warm and humid climatic zones. So coming to the structure of my presentation. So the presentation starts with background and context, that is the global challenges of building sustainability. And then we have research aim and objectives, which I talk about the literature insights. Then we have a methodology. So I have took a mixed methodology approach for the same. And coming to the key findings, so the key findings talk about green building rating tools variations and principal component analysis insights and passive strategy ranking were being the key findings from this particular research. And then we have expert insights from interviews, and the proposed framework would be shown, and then evidences from the case study, and coming to the conclusion and future scope of the study. So first, coming to the background and context. So the global challenges of building sustainability. So the construction sector is a significant contributor to climate change, with buildings accounting to almost 40% of global energy consumption and 36% of carbon dioxide emissions. To combat this, green building rating tools were developed to evaluate building sustainability metrics like energy efficiency, water conservation, and material use. However, these tools often fail to provide a standardized framework for assessing the passive design strategies alone. So passive designs which leverage natural resources like solar, heat and wind is crucial for energy efficiency and thermal comfort, particularly in warm and humid climates. In these regions, passive cooling techniques are vital as air conditioning can account for around 50 to 60% of energy demand. So the problem is that the current green building rating tools have significant inconsistencies in how they score and weigh these strategies. So coming to the critical research gap that was being identified. So the lead rating system emphasizes energy and water performances but underrepresents the passive design elements. BREEAM includes broader sustainability indicators but lack a clear provision for passive strategies. GRIHA aligns better with Indian climatic conditions but does not benchmark against global standards. And well rating system focuses heavy on indoor environmental quality but neglects energy optimization. These shortcomings hinders the effective integration of passive design in sustainable building practices, highlighting the need for the more robust and climate responsive framework. So coming to the holistic approach, so the aim is to create a comprehensive framework of passive design strategies that can be integrated into green building rating tools, evaluating their effectiveness in achieving energy saving, thermal comfort, and reduced carbon footprints. So the research objectives are five in number. Coming to the first objective is to develop a quantified framework for passive design strategies tailored to warm and humid climates. The second objective is to assess green building rating tools like LEED, BREEAM, GRIHA, WELL, etc. for their weightages, methodologies, and representation of passive design. The third objective is to quantify the performance data from case studies and simulations on natural ventilation, insulation, shading, and daylighting. So coming to the objective 4, it identifies to identify impactful passive criteria for energy efficiency, thermal comfort, and reduced carbon emissions through statistical analysis. And the objective 5 is to provide actionable policy recommendations for integrating passive design into green building rating tools. So, coming to the passive design integration in warm and humid climates and the green building rating systems gap and opportunities. So, the passive design strategies like natural ventilation, insulation, daylighting, shading, etc., are crucial for enhancing building performance in warm and humid climates, incorporating improving indoor environmental quality and reduced energy demand. So natural ventilation removes heat, improves air quality and lowers cooling loads, and thermal insulation minimizes heat transfer, significantly cooling energy consumptions. Daylighting conserves energy but requires careful balance with solar heat gain to avoid overheating. Shading devices block direct solar radiation, decreasing indoor heat gain and the energy demand. So while green building rating systems like LEED, BREEAM, GRIHA, and well these approaches, their emphasis on passive design strategies is varying between rating system to rating system. For example, if we take well rating system, it focuses on indoor quality but less on energy efficiency, while GRIHA rating system, despite it focus on Indian climate, still undervalues passive designs in its credit systems. So coming to the challenges in green building implementation, so inadequate climatic data and behavior variability is being found, and conflicting design goals and insufficient region specific assessment mechanisms are also being found from the literature study, and many green building rating systems remain indifferent to regional climatic nuances, creating evaluation gaps. So the National Building Code of India emphasizes the importance of early stage passive design assessment, highlighting its cost effectiveness and adaptability for occupant comfort and reduced energy use. So moving forward, green building rating systems must develop a climate sensitive research based framework that prioritizes passive design interventions to support a resilient low carbon built environment. So coming to the key phases of the methodology. So a mixed methodology approach was being taken up. So three phases were being taken. The first phase is a data collection, which we have both qualitative and quantitative data. So the qualitative data talks about semi-structured interviews with architects, consultants, and policymakers to gather expert insights on passive design implementation challenges. And the quantitative data is the case studies and the literature review provided empirical data on energy consumption, cooling loads, and thermal comfort metrics from warm and humid climatic regions. So coming to the statistical model, three statistical models were being explored in this particular research. The first one is a principal component analysis PCA method used to identify the most influential passive design variables. And coming to the second method, that is multi-criteria decision analysis MCDA, and AHP process, that is analytical hierarchy process, which is used to assign relative weights to passive design parameters based on expert judgment. Coming to the regression analysis, assessed the relationship between passive design variables and building performance indicators to identify key predictors of energy saving. And finally, coming to the framework development of our methodology. So it combined the PCA findings and HP based weights with quantitative performance data to create a weighted scoring framework. And the benchmarked the framework against existing green building rating tools to identify gaps and guide future assessments. So coming to our the first key findings of green building rating tools variation. So if we can see in the particular chart which is being developed by the author, so the score distribution was being shown on the x-axis, and on the y-axis different rating across all the countries were being taken up. So like ARZ rating system, the assessment standard of green building of China, the best rating system, GBC Brazil, DGNB, Green Star, GRIHA, IGBC, etc. And the scores distribution were being indicated through different color codings. So in that, the first one, that is our passive design strategies. So which is being given in the blue color to integrate and passive design. Then coming to orange one, which talks about the location and transportation plus sustainability sites and land use and ecology. The green indicates water, red indicates energy, violet indicates the material, brown indicates indoor environmental quality and health and well-being comfort, and the pink indicates innovation, the gray indicates management, construction impacts, process quality, and the green indicates the miscellaneous. So from the above chart, the analysis of 25 green building rating tools shows they interpret and prioritize sustainability differently based on their regional context. If we see the lead and BREEAM, so that demonstrates a relatively balanced scoring methodology, distributing emphasis evenly among key categories to provide universally applicable benchmarks. And if we take the regional tools, example like Singapore Green Building, Green Mark, and Tarshid, so that assigns greater weightages to the categories reflecting their climate specific and environmental issues such as water conservation and urban ecological integration. So from these key findings, the adaptive approach ensures the rating are not just a checklist but a true reflection of building performance in its specific environment. This highlights why a one size fit all approach is insufficient and reinforces the need for climate specific framework to evaluate and encourage the effective passive design. So this slide talks about the scores distribution of certifications across different categories. Moving to the next one, again from the key findings from principal component analysis variation. So we can see the different principal PCA scores were being there. Some are negative and some are positive scores for different rating tools. So to conclude the PCA findings, the PCA variations of key findings, and through analytical hierarchy process. So the AHP result shows that HPI, that is Home Performance Index Rating System, which got the score of 24.72, and ARZ, which got 23.06, leads in passive design emphasis, while lead, which gives a rating, which got the score of around 10.91, and GRIHA, which got a score of 9.96, exhibit limitations. So the regression analysis confirms passive design elements significantly reduce cooling energies. So when we take shading devices, it gives a variation or a reduction of around 18.2 kilowatt hour per meter square per year reduction. Coming to the wall insulation, it gives around 3 kilowatt hour per meter square per year of savings. The roof albedo, which is having 10.5 kilowatt hour per meter square per year of contribution, and natural ventilation, which has around 7.8 air changes per hour of improvement. So this is the PCA breakdown of each certification based on passive design strategies alone, which is again prepared by the authors. So coming to the PCA insights, so this is the PCA analysis of passive design strategies in sustainable building certification. So here also we can have some of the rating systems having a negative score and some of the rating systems having the positive score. So when we see how this GBRTs prioritize the passive design strategies, the PCA results reveal significant disparities on how certification system improves passive design strategies. The high scoring systems, that is the ARZ rating system, scored highest, which has a PC1 value of 3.84, DGNB, Home Performance Index, Pearl, and Green Mark, indicating a strong integration of passive design. Coming to the negative scores, which are going minus. So in contrast, when we take lead, GRIHA, IGBC, or GBC, Brazil, CASA, Lotus, Greenship, etc., scored negatively, reflecting weaker incorporation of these passive design elements. So the next one again is the key findings for the top performance in passive design. So here we can see on the x-axis we have the weighted score from 0 to 25 for the passive design alone, and the y-axis may we have different sustainable certifications, and this is ranked based on the weighted scores, which is again prepared by the author. So here we can see Home Performance Index and ARZ rating system ranked highest with scores of 24.72 and 23.06 due to their strong emphasis on passive design strategies, while lead and GRIHA, which was discussed earlier, receives moderate scores, indicating limitation of their responsiveness to climate adaptive design principles. And the regression analysis demonstrated that statistical significance of shading devices, wall insulation, and roof albedo in reducing cooling energy consumption, while model accounting for 82% in the energy use. So coming to the expert insights, the expert insights, so here we can see we have different expert insights. The purpose of interviews, it was conducted, the semi-structured interviews were being conducted with 20 leading architects, policymakers, and green building consultants who are doing their practice in the warm and humid climatic zones. The goal was to understand their practical challenges and perspectives on passive design implementation in warm and humid climates. So in warm and humid, the key insight one, if we can see the policy and practice gap, experts noted a significant disconnect between the existing green building rating tool requirement and the actual on-site implementation of passive design. So many standards are seen as theoretical and not practical. Coming to the key insight number two, the importance of local context. So the interviewers emphasized that successful passive design is highly dependent on local climate and cultural factors. A one-size-fits-all approach fails to capture these nuances, leading to the less than optimal results. So the key insight three, the need for education. The lack of widespread knowledge among builders and designers on how to effectively integrate passive design strategies was identified as a major to this particular adoption. So we have done some real world impact case study evidences again from the literature study itself, and the performance metrics of each case studies were also being shown, and this is also being prepared by the author. So here we can see the different case study locations, the passive strategies implemented, the cooling load reduction, indoor temperature reduction, energy saving percentages, and thermal comfort improvements. So if we can see the same, the cooling load reduction case studies in Indonesia and Gaza Strip showed passive design strategies reduces cooling loads by 35% and 59% respectively. And the temperature reduction, the integration of these strategies led to a 2.5 to 3 degrees drop in indoor temperatures also. And the energy savings, passive design resulted in energy savings of up to 29% and a significant increase in thermal comfort hours. Global versatility. So these findings highlight the effectiveness and resilience of passive design when tailored to the local climate and cultural context. So the finally coming to the proposed holistic framework. So this diagram is a framework diagram of passive strategies of warm and humid climates through expert opinion, which is again prepared by the author. So if we can see in this, the building energy efficiency through passive design, some of the variables were being taken. So the building envelope optimization, the key components of the above, the holistic framework, the building energy optimization focus on minimizing solar penetration and heat transfer through techniques like shading and fenestration design. Natural ventilation, so strategies to improve airflow such as optimal opening placement and consideration of wind direction and surface exposures. The third key component is a roof and wall insulation, which reduces heat transfer into the building by focusing on factors like thermal conductivity and R values. And the fourth key component, which is a material selection, uses innovative and climate appropriate materials like phase change materials, bamboo composites, and double skin facades to enhance the thermal regulations. So coming to the conclusion and the future scope, so here we can see a framework based on findings from the case studies and expert opinion, which is again prepared by the author. So the key findings are existing green building rating tools often lack sufficient emphasis on passive design, especially for warm and humid climates. Our study provides a data-driven holistic framework that integrates key strategies for a system-based approach. And the framework bridges the gap between theoretical strategies and the real-world application, offering scalable guidance for climate responsive architecture. And the case studies provide strong evidences of effectiveness of passive strategies in reducing the energy consumption and improving the thermal comfort. The way forward, if we can see the geographical validation, the framework needs broader geographical validation to assess its adaptability in various climates and context. The urban adaptability, future research should focus on financial feasibility and adaptability of these interventions in the dense urban areas where space is limited. The advanced tools like exploring and integration of AI-based design tools and performance-based assessment models for optimizing the passive design strategy should be used. And policies and incentives, the policy makers should be encouraged to provide policy support, financial incentives, and education to ensure widespread adoption. So these are the references, and I thank OIDA for giving me this particular opportunity in presenting my paper. And I also acknowledge the Department of Architecture, School of Planning and Architecture, Vijayawada, all the architects, consultants, and policy makers who provided their valuable insights. Thank you one and all for giving me this opportunity.